All right, so let's go on to our second talk, which will be given by Yuxiang Yang on optimal universal programming of unitary gates. It's over to you.
Thanks a lot. Can you hear me? Okay, thanks for the introduction. And I would like also to thank all the organizers and technical staff for successfully holding this conference. And today is my pleasure to introduce to you our recent work on optimal universal programming. And this is joint work with Renato Renner from ETH Zurich and Giulio Chiribella from the University of Hong Kong. So my talk is about programming, which is arguably one of the most important tasks of computing. In the classical region, programming could be really complex and difficult in details, but in a sort of abstract high level, it is simply about assigning different bit strings to different functions. So let's imagine you want to execute a particular function. Then what programming gives you is just instead a bit string that serves as identification of this function. And by inserting this bit string together with input data into the classical processor, processor would give you the computation outcomes. Then the task of programming in the classical world at very high level is about ways of designing this map from different functions to different bit strings. As you can see, different ways of assigning bit strings to functions would affect a lot the efficiency of doing so. So now that we almost have quantum computers, we also want to program quantum computers. So in a sense, you want to kind of give a way of inserting bit strings into quantum computers so that they could execute certain unitary as desired. A straightforward way is to kind of extend what we had in the classical world, meaning that we also use bit strings to represent unitary gates. And you can take the variational approach, for example, which divides a circuit into small blocks of unitaries, each controlled by some parameter. And whenever you want to execute a certain unitary, you just send into the processor a sequence of bits for the configuration of these parameters. As you see here from the right-hand side, unitary is a sort of a physical thing, which has continuous parameters, whereas in reality, everything is sort of discrete bits. So you end up having some approximation error. So a relevant question is, what is the programming cost? Naming that if one wants to achieve certain accuracy in the approximation, how many bits do we need to encode the program? And this is also the main focus of my talk. Let me give you a slightly more quantitative example. So way of programming in such a spirit. So you can take the famous Solovay-Kitav algorithm, which was used to show the power of discrete universal gate set. So essentially, what the algorithm does is that given an arbitrary universal gate set, arbitrary error threshold, the maximum error you could tolerate, and an arbitrary input unitary, it gives you a sequence of gates, each of them contained in the universal gate set. And this length of this sequence of gates is polylogically in 1/epsilon. And by concatenating this sequence of gates, you end up with an epsilon well approximation of this input unitary. Okay, and one can see quite straightforwardly that this gives us a way of constructing programming, namely that this sort of gate synthesis particle. So what you could do is just to use the output of Solovay-Kitav algorithm, right? Whenever you want to program a unitary U, you just first look at its decomposition given by the algorithm. And then you could kind of assign a tag to each gate in the universal set. And you just use this sequence of tags as your program. So the quantum processor will just read off this sequence of bits and execute the gate corresponding to each of the tags. And the programming cost of such a protocol scales also polylogically in 1 over Epsilon. So given this example, there are a few questions that naturally follows. The first is whether this is already the best we could do. Can we have even smaller costs fixing the accuracy, or even can we achieve exact programming without any error? And the next level question is that we have always been using, like so far, classical bits as programs. But since we are doing quantum information processing, we are basically allowed to use qubits rather than classical bits. So is there any advantage at all of doing so? So if we use quantum programs, is there a better, let's say, programming cost trade-off? And in my talk, in the following, I'll give answers to all these questions. So the task we consider is the universal programmability of quantum gates, meaning that we want to implement any unitary of a fixed dimension in a programmable way. So what we need to do is to design a pair of quantum channel and as well as a set of quantum state psi u. And this quantum state psi u serves as a program for each unitary, in the sense that whenever one wants to implement run a particular unitary u on arbitrary input, quantum input phi, what she needs to do is to insert both input and the program states into the processor, which runs this quantum channel C jointly on them. And the target is to have the output correctly as the computation output. And the universal here means that the action of the processor C should not contain any prior information about a particular U. So it should not cheat. And all the information of particular U you want to execute should be contained in the program, which serves sort of as a capsule of information. So in this, for this universal programming problem, however, the first result known is no-go result, proven by Niels and Trong many years ago. And what they show is that if one allows for programming arbitrary unitary of fixed dimension, and also without any error, then the programs they use must be infinite dimension, must have infinite quantum dimension, and therefore unphysical. But whenever we have no-go results in quantum information, like no cloning, for instance, there is always some way out. So for instance, you could consider approximate cloning rather than exact cloning, sorry. So we can do the same thing here. So we can consider approximate programmability, which means that we now allow a small error in terms of diamond norm or arbitrary norm that you want in the output of the computation. And by doing so, actually, you have already seen from the previous example based on Solovay-Kitaev algorithm that the programming cost, CP, which is the number of qubits needed to encode the program, can be made finite. In the previous example of the Solovay-Kitaev motivated algorithm, this cost would be polylogically in 1 over Epsilon. And I would like to also note that there are other ways of circumventing no programming theorem. For instance, if you allow for a small chance of failure, meaning that the whole process is in general probabilistic, then you could still, with some chance, achieve perfect programming. But for my talk, I'll just focus on deterministic and approximate case. Okay, so in this case, the key problem in this case can be formulated as the following optimal programming problem, which means that we focus on the case where we fix the dimension of all the unitary to program. So we just want to program all unitaries of a fixed dimension. And in this setting, we ask the question that what is the optimal trade-off between Epsilon, which is the error threshold, and CP, which is the number of qubits you need to encode the program state. And this has been an open problem for a really long time, since its first proposal, also by Niels and Zhang in the same work. And you can see here, despite all these nice pieces of work, there hasn't been really a conclusive answer to this question. And such an answer would can serve for the first place some sort of resource quantification of implementing quantum computing. So let's imagine if we have an affirmative answer to this problem and we know what is the optimal trade-off curve, then once you have any practical approach of programming, so it could be very complex in details and very realistic, you could always compare its performance to this optimal trade-off curve and to see how far you are from the optimal. Because in practice, usually the protocol we execute would not really be the strictly optimal one. But if we know that we are not too far away from the optimality, then I think you can conclude it's a very good protocol. Despite this immediate impact, the optimal programming problem also gave rise to other interesting quantum information processing protocols. For instance, the port-based teleportation protocol, which I believe you are now very familiar with from the nice talk that we just had, was actually first proposed by Ishizaka and Hiroshima to solve the optimal programming problem. But the protocol later has found many applications that are also very interesting, as you also learned from the last talk. And at last, giving a solution to this optimal programming problem, which concerns programming of unitaries, you could as well consider a programmable structure for other quantum instruments like channels and measurements. And there are also independent lines of research. Okay. I hope I've convinced you that this is a meaningful problem with a lot of implications. So what needs to be done next is to solve it. And this is exactly the main result of our work. So in this piece of work, we give an affirmative answer to this optimal programming problem in the sense that we identified the cost accuracy trade-off to be of the following form. So in leading order, the cost of programming, which again is the number of qubits you need at least to encode the program, would scale in the leading order linearly with log 1 over epsilon. So compare, as you recall from the Solovey-Kitov inspired algorithm, which is polylog, we now here have a linearity in log 1 over epsilon. Also, we identify the prefactor here to be quadratic in the dimension of the unitary. So intuitively, the larger the unitary is, the more difficult it is to program it. And moreover, in order to achieve this optimal trade-off, we use genuine quantum states as programs rather than strings of bits. So this also kind of provides an answer to the last question, that there is a sort of quantum advantage in such a task. So the way we prove this problem is by showing both an upper bound and a lower bound in the programming cost in terms of the accuracy. And compared to both bounds, when compared to the best known prior results, improve them by a fair amount. And most importantly, our upper bound and lower bound converge for the first time ever. And that's why we can claim that we have an answer to this question. So for the remaining of my talk, I'll show you some brief ideas about the proof of both bounds. So let's first start with lower bounds, which is sometimes called the impossibility proof, or the converse part in quantum information theory. And the key ingredient of showing this lower bound on programming costs is something called quantum resource recycling lemma. And this lemma essentially says that the quantum resource that one put in quantum state to implement any unitary can be recycled. So after its use, you can actually reuse the output to program to execute this unitary more times. And in the context of programming, it essentially says the following. So given an arbitrary approach of programming, so this is totally arbitrary. So imagine somebody gives you a black box access to program the program states and a set of program states and the action, which is channel C of the processor. And it is guaranteed only that the processor, when acting upon program, would simulate one use of a unitary u up to epsilon arrow. And what the quantum recycling resource recycling lemma says is that we can always find another quantum channel n, which is larger and can be constructed based on C, such that when you apply this n to the same program states, it will give you not only one use of u, but m parallel uses of u, with m being arbitrary. Of course, this does not come for free. So the price to pay is that now with the n, if you use n, then the approximation arrow to this u tensor m would now not be worse. So it actually grew linearly in m and root of epsilon. Okay, so this means that you could not recycle it forever, and there is some limit, some stage at which the approximation precision would be too bad to continue. Okay, and this is first of all a totally quantum feature, because the proof of the recycling lemma, which unfortunately I don't have time to tell, relies on purification of quantum processes. And also a key thing is that this only holds whenever you are trying to implement a unitary operation. If this thing is a quantum channel, then the argument would fail. So this is totally quantum feature. If you're considering a classical counterpart of using resources to implement classical gates, you wouldn't get the same results. And as I hope you could already see from my description that this actually holds beyond the problem of programming. Actually, we show that it can be applied to other more general resource theories. We have a detailed discussion of this in an independent work by us. And this work has also been presented at last year's QIP. So if you could manage to find my talk at last QIP, you could have a look. Okay, back to the problem of programming. So thanks to the quantum resource recycling lemma, if you are given arbitrary pair of program and process action that is designed to program only one use of u to a good precision, then the recycling lemma implies that by using the same program, you could actually program many uses of the same unitary, actually 1 over root epsilon copies of the same unitary before the precision goes too bad. Okay, and the intuition is that the program, even if it's designed only to program one use of u, needs to have very large size, because the recycling lemma requires to also serve as a program of many uses of u in small epsilon region. So it needs to have, it needs a system whose size would kind of rule with the precision of approximation. And we can actually make this quantitative without too much difficulty. For instance, we use the whole level information as a quantification of information. And we show that m uses of an arbitrary unitary u have approximately d squared minus 1 log m qubits of information about this unitary. So by having many uses of the same unitary, of course, your knowledge of this U grows. But it does not grow really linearly with M because you are just repeating the same unitary. So it grows actually logarithmically in M, and as described by this approximation. And finally, by insert 1 over root epsilon into this equation, we actually get the lower bounds. Okay. So this concludes the sort of intuitive proof of the lower bounds. So what remains to be done is to have an upper bound. So to show an upper bound, which is sometimes called direct parts in information theory, what you need to do is to construct a concrete particle and argue that the performance of the article is as such. And in this case, to solve the optimal programming problem, what we need to do is to come up with a sort of optimal programmer whose performance matches the description of lower bounds. So this requires us to follow really sort of the intuition of lower bounds proof. And recall that from the recycling lemma, we know that if a program, even if it is designed to program only one copy of U, if it's good, then it needs to be able to sort of serve also as the program for many use of the same unitary, right? So following this intuition, we'll just prepare the program of our optimal approach in such a way, namely that we prepare our program by learning, by shining n uses of the same gauge U on a suitable quantum states. And this is how the programs of our protocol is prepared. And in order to execute the unitary after having a program input, the processor will just perform a measure and operate approach, which means that the processor would perform a suitable PUVM on the input program, which gives the processor an output, which is an estimate of this unitary, and it will just execute the corresponding unitaries on the quantum input data. And you can see already here that the source of error of our protocol comes from the error of estimation, actually. This is because you are trying to estimate a unitary from an input. So no matter how large this input is, there will always be an error in estimation. And if you're familiar with quantum metrology, you can already identify a subroutine here, which is a standard setting in quantum metrology. That is, you need to design a pair of quantum probe states and PUVM such that you could estimate a unitary from many uses of it. So we conclude that the performance of our protocol, the optimal programming protocol, can be achieved by learning via quantum metrology. And what remains to be done is actually to solve this metrology subroutine, namely to come up with good probe state and PUVM. And what we did is that we come up with a new class of quantum states for this purpose. And this is a multi-parameter quantum metrology task, essentially tomography of SUD unitaries. And for this purpose, we come up with a new class of quantum states, which extends the optimal quantum clock states proposed many years ago. And we use this new class of quantum states to finish our objective. And I don't have time to tell you about details of these quantum states, which is constructed based on SUD irreducible representations, but it has high performance in metrology and can be used in other applications. For instance, we use it to construct approximately covariant quantum error correction code in an independent work. Okay, so to wrap up with the performance of our metrology protocol can be strictly upper bounded by the following. And as you can see here from the upper bounds, the leading order in terms of the accuracy, which is 1 over epsilon, is exactly the same as predicted by the lower bounds. And therefore, in the low arrow region, we conclude that the upper bound would converge to the lower bound, and therefore we have a solution to the optimal programming problem. Okay, so now I have to wrap up my talk. So the take-home message is that I've shown to you the solution to the optimal programming problem, and by showing to you the cost accuracy trade-off as the following. And of course, this does not close the field of programming. Actually, there are actually many meaningful open problems here. For instance, here we focus on trade-off between accuracy, epsilon, and programming cost. This is for a kind of fixed dimension unitary. But you also want to consider programming a large quantum computer in the future, where it is kind of more meaningful to fix first the arrow and then consider the trade-off between the programming cost and dimension of this computer, and for which there is still no answer. And also you can observe that this d-1 quantity here is exactly the number of real parameter you need to parameterize unitaries of d dimension. So we can conjecture that if we want to program now a subset of d-dimensional unitary S, so for instance, you can consider programming all the phase gates of d dimension, then the programming cost, the optimal programming cost, would still have the same, follow the same expression, with d-1 now replaced by the number of parameters you need to parameterize this subset. Okay, I guess with this, I'll stop here and thank you for your attention.
Thank you, Yuxiang, for the very nice and instructive talk. I feel I learned a lot. So we have some questions from Slack. Mars was also asking if you could say more about why it only works for unitaries, but not arbitrary channels, and why couldn't we just implement the Steinspring isometry and then trace out the other system?
Oh, I guess you are talking about the lower bounds proof, right? Actually, this recycling lemma. And this is a very good question. There is no very, let's say, short answer to it. I can say more in the round table, but the thing is that we need to, this proof relies heavily on the purification of quantum processes. And the key thing that distinguish between the case where this U is pure and you have a generic quantum channel is that if you consider purification of these processes, then let's say, if you want the overall action of program processor to simulate a unitary, then you kind of needs to make sure that the environments after the action have very weak correlation with the unitary. Otherwise, you end up with this mass of mixture of unitaries, right? So, but if you want to simulate a channel here, then there's not necessarily this restriction. And this restriction is the key to getting such results.
Right. Thank you very much. So there are more questions on Slack, but we will go on with the next talk because of time. But Yuxiang, maybe you can go over to answer the questions. And also, of course, afterwards, we have the round table and everyone is very welcome.
Okay, sure. Thanks a lot, Laura.
Thank you.